So we have talked about how to define my variables. We've talked about constraints and how you might be able to apply a change of variables either to your constraints or to how you actually define variables. And the next topic is, it's just one slide, but it's to point out that quite often when you do engineering optimization, you might have analyses that are quite expensive. It could be a finite element analysis, it could be CFD, computational fluid dynamics, or any other expensive evaluation. Now, a lot of optimizers do a lot better when you have derivative information. The challenge with using these expensive simulations is that quite often you do not have derivative information. And if you have a lot of variables, then doing something like finite differences is not going to be efficient. And so in this case, I had a finite element analysis. You see a couple of differences, like ideally, I have a nice smooth angle distribution. As manufactured, you actually have the machine doing these paths. And so the finite element model that I had a different element definition for every single element, which made it even more computationally expensive than a regular finite element model already is. And so some of the problems you would have is that you don't have the derivatives. Some of the functions like buckling modes or buckling values might not be smooth. Sometimes you might have to pick a maximum stress or a maximum strain somewhere because you can't possibly look at the strains or stresses in every single element in your model. And so, the results might not actually be nice and smooth. And so one remedy for this is to generate a surrogate model for the quantities of interest. So in this case, I had something that looked at the buckling mode. I had something that looked at or kind of calculated the strength of the model, etc. And during the optimization, the surrogate model helped in terms of convergence. I used a very specific Boeing proprietary program that has some other smart features to look around in your design space. But typically, you can use nowadays neural networks, Kriging models, Bayesian models, different kinds of basically model fits to your quantity of interest, and then use those during your optimization to speed it up. And you always still want to make sure that the results that the surrogate model spits out, especially for your optimum result, matches the actual simulation, right? But during the optimization, you can get to your optimum point a lot faster than if you would just use your very slow engineering analysis by itself. Now, once you're done optimizing, there's one big question left, and that is, does my result actually make sense? Can I believe what I see? I'm going to give you an example. So this presentation is actually based on my PhD work. And before I started looking at this cylinder in bending, I was looking at a cylinder that I was going to compress actually. So basically, if you have your cylinder vertical, you would push it up and down and squish it. And I said, okay, well, let's do the optimization that I just described, but then for actual compression. And my optimizer gave me 60% improvement in performance. And I'm like, wow, that's a lot. I wonder what explains it. And I'm like, no, it had certain extra stiffness near the boundaries. I thought, well, maybe that kind of helps reduce the length of the buckles, but I couldn't really explain it. We manufactured a cylinder based on those definitions, and I must have been looking at the next optimization, and I discovered that I had a programming error. I had a bug. a factor 2 or a plus or a minus, something very similar, simple, right? And I discovered it. It was, and then I had to tell my advisor, hey, I found this bug. And could I have done something more to look at the results and say, I can't explain it, maybe I shouldn't trust it. If it's too good to be true, it probably is. In the end, I was going to present the results at 2 different conferences, one in Hawaii, one in Paris. But I decided to withdraw the paper because when I reran the optimization, I didn't actually get a result that was better than my baseline. There was no improvement at all. And so, it kind of, hurt my feelings at the time. I didn't get to go to these really cool places, but it saved my career, in hindsight. So I'm glad I made that decision. But it did teach me this very valuable lesson. If you can't explain your results, you better triple check. Because, again, if it seems too good to be true, it probably is too good to be true. So what can you do to validate your results? Here are a couple of things that you can do. It's not an exhaustive list. It's going to depend on the actual problem that you're working on. But typically, you might want to start with a hypothesis. What do you think the optimization result is going to show you? The best compliment I've had doing an optimization at Boeing, where typically it was kind of a manual process. The person who did the manual process at the end said, when we showed them the optimization result, I could have drawn this up, except that we got an improvement that they had never gotten by hand. But the fact that he said, I could have drawn this up, kind of gave me the confidence that what came out actually kind of made sense. And it wasn't outside of what an engineer who did that for his daily job would have come up with. So, a hypothesis is, this is what I think is going to come out, and then you can compare it. Engineering judgment is really like, if I'm optimizing a thickness, let's say of a fuselage skin, and it says 10 inches, that doesn't really seem to make sense because our thicknesses are not 10 inches. However, when you're talking about a submarine, those numbers seem right. So it does depend on your application. And then, I think the most important thing, after your hypothesis is looking at detailed simulation results. When you run an optimization, you tend to look at your convergence plots and say, oh, look, it's converging, etc. Oh, look, this final result is so much better. But we often forget to go back and look at this optimum result. Look at things like stress or strain fields or flow fields, if you talk CFD, displacements, buckling modes, other data. If it's geometry, you actually want to plot the geometry and make sure it makes sense. Again, an example that I've run into was, hey, we had this awesome result that saved a lot of drag. And then we plotted the geometry, and there was this huge spike in the geometry, which is like, well, obviously, this is nonsense. Well, if we hadn't looked at it, it might not have popped out. So quite often, when you get a really good result, you either have a programming error like I had, or you might have missed a constraint. And again, talking to engineers, and if they're trying to describe the thing that they typically do by hand, there are a lot of implicit assumptions that they don't even realize they made. And if you don't put those in your optimizer as a constraint, the optimizer will find those kind of weak spots in your formulation and go straight to it. And of course, the final validation is to actually build and test the thing that you optimized, which still doesn't tell you it's the best thing, but it might at least tell you whether the result is better than maybe your baseline. So I will walk through a couple of these, again, for this particular example, and then we'll wrap up. So in this case, we have the cylinder in bending. So you might think of it as a beam, right? If you have an I-beam, you might want to say, oh, I think it's going to be stiff on the top. So T0 is going to be stiff. Small angles in this case corresponds to high stiffness. On the bottom, I think it's going to be stiff. And on the side, if you have an I-beam, it's going to be shear. So we're going to put 45 degrees or plus or minus 45 degrees. This is another funny anecdote. I was at a conference once where I was presenting the results of my research, where I optimized the cylinder in bending. And the gentleman before me was from NASA. And he designed a beam for bending, not using an optimizer. And this is basically the design he came up with. Now, it had different number of layers, etc., but the concept was exactly this. Now then, I did my optimization, and I looked at the results. And so, what did I get? I had 3 steered layers, and all of them had small angles for T0 through T2. So basically, the top half of my cylinder was very stiff. Great, that's what I expected, right? But I also expected kind of more like 45-ish numbers on the sides, T2. And that's not what I see here. They're still pretty small numbers. And I thought, okay, well, an I-beam is usually designed for both shear and bending. But in this case, I only have pure bending. So I don't actually have shear. So they don't need to be plus minus 45 on the sides. So, okay, that one was explained. But then the compression side here, the angles were much bigger, which means that the structure was not very stiff in that location where I had expected it to be stiff. So there was this, like, I'm not quite sure, right? And I didn't have as much experience as I have now, although it might not even have been obvious if I had had that experience. So then what did I do? This is showing a couple of different things that I did. In the middle, what you see is kind of this illustration of these fiber paths. The horizontal axis is the length of the cylinder. So it's basically, kind of if this was the cylinder like this, it's unrolled and it's kind of like in this vertical orientation. And it's just a way to make visualization easier. Now, on the left-hand side is basically the strain. And we assume that the cylinder was kind of capped. And so it's a sine or cosine function, as function of the circumferential coordinate. And so the vertical axis is this circumferential coordinate. And right here, let's see where my hand is. Right here in the middle is kind of where the compression side is. And then the tops and the bottoms of these plots represent the areas where you have tension. So what happens is, with structures, the stiffer your structure is, the more load it tends to attract. And if the stiffness was the same all around the circumference, your load distribution would look the same as the strain distribution. But the stiffness was not constant because we changed these fiber angles around the circumference. And what happened is it made it really soft right here in the middle. And you can kind of see that in the dip right here, where it's, hey, I'm not going to carry all the load here in the middle. I'm going to have the sides of my cylinder actually contribute more by making the center softer. Well, what that resulted in is, if the very bottom of the cylinder has the highest load, that's where it would start buckling. But it's only a very narrow region of the cylinder, and I'm going to go over here where you can see these buckling shapes. The buckling shapes on this cylinder actually span a pretty big portion of the bottom of the cylinder. And that's because the load is spread out, because I made the stiffness of this very bottom point lower, and this bigger portion of the cylinder helps carry the loads. And so it can now carry a much higher overall load before it starts buckling. Now, that's quite detailed in terms of this result, but what I'm trying to illustrate is, in order to come to the conclusion that the result actually made sense, is that I looked at the strain distributions. Then I combined that with the definition for my laminate to look at the internal load distributions. And I looked at the buckling modes to kind of draw the conclusion that this result actually does make sense. And so it wasn't just looking at that one buckling number that was better. It was really looking at all the information I had available to kind of build that confidence. I wasn't going to make the same mistake twice and miss out on more fun locations to go present my work. So that's the how to make sure that things make sense. I have one kind of go back slide here, reflecting on my question of how many variables should I use in my optimization? Is more better? And in order to illustrate that, I had 3 case studies here that I actually ran optimizations for. The top one was just my baseline where there was no steered layers at all. The second row here, there were 5 steered definitions, which means there were 20 total plies. But with 5 variables per ply, the total number of variables in this optimization was 25, which was more than the third row and the fourth row, which had 15 and 10 variables, respectively. So again, in theory, you'd say, hey, the more variables I have, the better the result. But if you look at the improvement compared to the baseline, row 3 actually did better, even though it only had 2/3 of the number of variables from the second row. Now, why is that, right? In theory, more variables is better. Well, there are 2 possible explanations. The third row actually is not a subset of the second row. If you look at the second fiber, steered fiber layers, plus minus phi 2 in this case, you cannot achieve by doing 0.90. Or you cannot achieve 0.90 with a plus minus layer, because it would always be, locally it would be plus minus 10, plus minus 12, plus minus 40, but you'll never get 0.90. So the third row actually is not a subspace of the second row. They're different design spaces. And one of the constraints which I didn't talk about in this lecture actually was very hard to satisfy with the second option here. But the third one here, the 0 and 90 kind of got me very close to the kind of the feasible space, almost by definition. And so the optimizer, within like 1 or 2 iterations found a feasible point, whereas the one above it might not even have, well, it did get to a feasible point, obviously, but it had a much harder time finding feasible positions. Now, the other reason is that when you have more variables, your optimizer might be more likely to get stuck in a local optimum. And so the algorithms I used did have kind of more global search functions embedded, which help to minimize that problem, but it still might happen. And then the final validation, this was just to show you some fun pictures. I tested them. It was nice correlation with the simulation. So all of that was great. And with that, I'm going to summarize this example. Whenever you set up an optimization problem, try to make use of symmetries to reduce your number of variables and your number of constraints. If it is appropriate, you might want to apply a change of variables. Again, that could apply either to your variables or to your constraints. If you have a very expensive analysis, you might want to use surrogate models to help get a smoother and faster evaluation. And remember that more variables is not necessarily better. Think about what you really need and try to balance that with having more design freedom. Finally, make sure you understand why your optimizer is giving you this better result, because garbage in is garbage out. So use your engineering knowledge and judgment to define your problem and to check your results. Thank you.